Hey everyone, and welcome. Today, we're going to dive into the two foundational pillars of calculus, derivatives and integrals. These concepts might seem like separate ideas at first, but by the end of our session, you'll see how beautifully and powerfully they're connected. Our goal is to understand not just what they are, but why they're essentially two sides of the same coin. We'll break this down by first mastering derivatives, then integrals, and finally, we'll reveal the incredible link between them. Let's get started. First up, derivatives. At its heart, a derivative measures how a function is changing at any given point. Geometrically, you can think of it as the slope of the tangent line to a curve. Algebraically, it's the instantaneous rate of change. Our objectives for this part are to define the derivative using the limit definition, and then to efficiently solve for derivatives using power and product rules. So, by the end of this section, you will be able to define the derivative and compute derivatives of more complex functions. Let's start with the formal definition. It all comes from the idea of limits. Remember the concept of an average rate of change? That's just the slope of a line between 2 points. To get the instantaneous rate, we imagine bringing those 2 points infinitesimally close together. This gives us the limit definition you see on the board. The derivative of a function f at a point x, denoted f prime of x, is the limit as h approaches 0 of the slope between x and x plus h. In other words, it's the limit of the average slope as the interval gets infinitely small. This definition is the foundation of the entire field of differential calculus. Calculating derivatives from the limit definition can be a bit cumbersome. Luckily, there are a few handy rules. Let's start with the simplest, the power rule. The power rule is our first shortcut. It states that if your function is x raised to some power n, its derivative is n times x to the power of n minus 1. That's it. Bring the exponent down and multiply, then subtract 1 from the exponent. Let's work through 3 examples to see it in action. For our first example, let's find the derivative of the polynomial x cubed plus 5x squared minus 2x plus 10. We can apply the power rule term by term. For x cubed, we get 3 times x squared. For 5x squared, the derivative of x squared is 2x, so we get 5 times 2x, which is 10x. For negative 2x, the derivative of x is 1, so we get negative 2, and the derivative of a constant like 10 is always 0. So the derivative, f prime of x, is 3x squared plus 10x minus 2. Notice how we just applied the rule to each part of the polynomial individually. Here's our second power rule example. What if your function has radicals, or is a fraction? Let's find the derivative of the square root of x plus 1 over the cubed root of x. The key here is to rewrite everything as a power of x. The square root of x is x to the 1/2 power. The cubed root of x is x to the 1/3 power, so 1 over that is x to the negative 1/3 power. So our function becomes x to the 1/2 plus x to the negative 1/3. Now we can use the power rule on each term. The derivative of x to the 1/2 is 1/2 times x to the 1/2 minus 1, which is negative 1/2. The derivative of x to the negative 1/3 is negative 1/3 times x to the negative 1/3 minus 1, which is negative 4/3. Putting it together, f prime of x equals 1/2 times x to the negative 1/2 minus 1/3 times x to the negative 4/3. See how transforming the function first makes it easy to use the power rule? Our third power rule example shows how you might need to simplify first before applying the rule. Let's find the derivative of the quantity x squared minus 1 times the quantity x plus 1, all divided by x. It's tempting to jump to the quotient rule, but let's be clever. Notice that x squared minus 1 is a difference of squares. It factors into x plus 1 times x minus 1. So our numerator is x plus 1 squared times x minus 1. This looks much more complicated. Let's try simplifying differently. Let's expand the original numerator first. X squared minus 1 times x plus 1 is x cubed plus x squared minus x minus 1. Now we divide that entire polynomial by x. This gives us x squared plus x minus 1 over x, which we can write as x squared plus x minus 1 minus x to the negative 1. Now it's a simple polynomial, and we can apply the power rule to each term. The derivative is 2x plus 1 plus x to the negative 2, much faster than using the quotient rule, which you may or may not remember right now. Always look for ways to simplify before differentiating. Sometimes, you just can't simplify. That's when the product rule comes in handy for differentiating the product of two functions. The product rule is for when your function is the product of two other functions, u and v. It says that the derivative of u times v is u times v prime plus v times u prime. In words, the first function times the derivative of the second plus the second function times the derivative of the first. There's a nice symmetry to it. Let's work through some examples. Let's find the derivative of the product x cubed times 2x plus 5. Here u is x cubed and v is 2x plus 5. So u prime is 3x squared and v prime is 2. Now we plug these into the product rule formula. We get x cubed times 2 plus 2x plus 5 times 3x squared. Expanding this, we have 2x cubed plus 6 cubed plus 15 squared. Combining like terms gives us our final answer, 8x cubed plus 15x squared. Here's our second product rule example, involving a couple of different function types. Let's find the derivative of e to the x times the sine of x. Here, our first function, u, is e to the x, and our second function, v, is sin of x. So u prime is e to the x, because the derivative of e to the x is just e to the x, and v prime is cosine of x. Now we apply the product rule. We have e to the x times cosine of x plus sine of x times e to the x. We can factor out the common term, e to the x, to get e to the x times the quantity cosine of x plus sine of x. Simple, right? For our final derivative example, let's look at one involving the quotient rule and see how it relates to our previous work. Let's find the derivative of 3x plus 1 divided by the quantity x squared minus 2. This one is a perfect fit for the quotient rule, which I'll write on the board. The quotient rule says the derivative of u divided by v is v times u prime minus u times v prime, all divided by v squared. A common mnemonic for this is low d high minus high d low all over low squared. Let's identify our parts. U is 3x plus 1, so u prime is 3. V is x squared minus 2, so v prime is 2x. Now we plug these into the formula. We have x squared minus 2 times 3 minus 3x plus 1 times 2x all over x squared minus 2 squared. Now we just need to expand the numerator and simplify. That simplifies to negative 3x squared minus 2x minus 6 all over x squared minus 2 squared. If you think back to our third power rule example, we saw how you could rewrite a fraction as a product using a negative exponent and then use the product rule. This is the more direct method for this kind of problem. Let's quickly recap our objectives for this section. We aim to define the derivative and compute derivatives of more complex functions. We successfully did this by starting with the limit definition and then using the power and product rules. You now have the tools to differentiate a wide variety of functions. To solidify your understanding, here are a couple of practice problems. Pause the video and give them a try. The solutions will be revealed shortly. And here are the solutions. I hope you got them right. Great work. Now, let's move on to the next major concept, integrals. Welcome to Part 2, the integral. If the derivative tells us how a function changes, the integral is about accumulation. It answers the question, what's the total amount or value accumulated over a period? Geometrically, you can think of the integral as the area under a curve. It's the opposite of a derivative in a sense, and we'll see why very soon. For this section, our objectives are to understand the connection between derivatives and integrals, to define both definite and indefinite integrals, and to use the fundamental theorem of calculus to solve them. So we're going to use the power of the fundamental theorem of calculus to find areas and antiderivatives. Let's dive in. We're starting with the indefinite integral. This is the simplest type of integral. It doesn't have a starting and ending point. Instead of asking for the slope of a curve, we're asking for the function itself. We are, in a sense, undoing differentiation. An indefinite integral of a function f epic gives us the most general antiderivative. We use this elongated s symbol called the integral sign. So, if the derivative of a function f(x) is fx, then fx is the antiderivative of fx. For example, the antiderivative of x cubed is 1/4 x to the fourth. Why? Because the derivative of 1/4 x to the fourth is x cubed. A crucial detail here is the plus c. The derivative of any constant is 0. So, the antiderivative of x cubed isn't just 1/4 x to the fourth, it could be 1/4 x to the fourth plus 5 or minus 10 or plus pi. We represent this arbitrary constant with c, the constant of integration. It's a reminder that there's not just one, but a whole family of functions that have x cubed as their derivative. Our first example is to find the integral of x squared plus e to the x minus 1 over x. Integration is linear, just like differentiation, so we can integrate each term separately. The integral of x squared is 1/3 x cubed. The integral of e to the x is e to the x. The integral of 1 over x is the natural log of the absolute value of x. So our answer is 1/3 x cubed plus e to the x minus the natural log of the absolute value of x, plus our constant c. This single function represents an entire family of antiderivatives. Now let's turn our attention to the definite integral. This is where we talk about area under a curve. The definite integral calculates the signed area between the curve f guess x, the x-axis, and two vertical lines, x equals a and x equals b. The notation looks similar, but notice the a and b on the integral sign. These are our bounds of integration. Conceptually, you find this area by dividing it into infinitely many, infinitesimally thin rectangles and summing their areas. This process is called Riemann summation, and it is a beautiful piece of mathematical history. But practically, we don't do that every time. We use the most profound theorem in calculus. That theorem is the fundamental theorem of calculus. It connects the antiderivative we just talked about to the area under the curve. It says that if f is any antiderivative of f, then the definite integral from a to b is just f of b minus f of a. In other words, you find the antiderivative, plug in the upper bound, and subtract the result of plugging in the lower bound. It's a game changer. Let's find the integral from 1 to 2 of 4x plus 3. The first step is to find the antiderivative. The antiderivative of 4x is 2x squared, and the antiderivative of 3 is 3x. We don't need the plus c here because it would just cancel out in the FB-FA subtraction. So we have 2x squared plus 3x. We evaluate this from 1 to 2. This is often written with a vertical line on the right. Now we plug in 2 for x and subtract the result of plugging in 1 for x. That's 2 times 2 squared plus 3 times 2, minus the quantity 2 times 1 squared plus 3 times 1. This evaluates to 14 minus 5, which is 9. The area under the curve y equals 4x plus 3 from x equals 1 to x equals 2 is 9 square units. Let's look at a definite integral where we might get a negative result. Consider the integral from 0 to pi of cosine x. Remember what I said about signed area? Let's look at the graph of cosine. From 0 to pi, the curve goes above the x-axis, then crosses and goes below the x-axis. The area from 0 to pi over 2 is positive. The area from pi over 2 to pi is negative. This integral will calculate the net area. First step, find the antiderivative of cosine x, which is sine x. Now we evaluate sine x from 0 to pi. That's sine of pi minus sine of 0. Sin of pi is and sin of 0 is 0. So the integral is 0. This makes perfect sense with our graph. The positive area exactly cancels out the negative area. The net signed area is 0. For our third example, let's explore an integral that might seem a little unusual at first. Let's find the integral from -1 to 1 of x cubed dx. Again, let's think about the graph of y equals x cubed. This is an odd function. It's symmetric about the origin. The area from -1 to 0 is negative, and it's a perfect mirror image of the area from 0 to 1, which is positive. Let's see if the calculation confirms our intuition. First, find the antiderivative of x cubed, which is 1/4 x to the fourth. We evaluate 1/4 x to the fourth from -1 to 1. That's 1/4 of 1 to the fourth, minus 1/4 of -1 to the fourth. Both 1 to the fourth and negative 1 to the fourth are just 1, so we have 1/4 minus 1/4, which equals 0. Just as we expected, this is a neat property of odd functions integrated over a symmetric interval. Okay, let's recap this section on integrals. We define the indefinite integral as an antiderivative, which represents a family of functions. We then define the definite integral as the signed area under a curve, and we learned how to compute it using the fundamental theorem of calculus by finding the antiderivative and evaluating it at the bounds. Here are 2 practice questions for you. Try finding both an indefinite integral and a definite integral. Pause the video now to work on them. And here are the solutions. I hope you're feeling more comfortable with both types of integrals. You've done great so far. Now for the grand finale. We've arrived at our final section, and it's the most important one: the connection between derivatives and integrals. By the end of this part, you'll be able to clearly explain why derivatives and integrals are inverse operations. So let's explore this beautiful relationship. The whole idea of derivatives and integrals being opposites is what's formalized in the fundamental theorem of calculus. It essentially states that the processes of differentiation and integration are inverses of each other, much like addition and subtraction, or multiplication and division. There are actually 2 parts to the theorem, but the one we've been using is the second part, which provides a straightforward way to evaluate definite integrals. Let's think about this. What does it mean for them to be inverses? It means that if you start with a function, differentiate it, and then integrate the result, you should get back to your original function. For example, if we start with x cubed plus 5x plus 2, and we take its derivative, we get 3x squared plus 5. Now, if we take the indefinite integral of that result, 3x squared plus 5, we get x cubed plus 5x plus our constant c. The constant of integration c is there because we lost the information about the original constant, a2, when we differentiated. This shows that the 2 operations undo each other. So, we've come full circle. We started by defining the derivative as the instantaneous rate of change and the slope of a tangent line. Then we defined the integral as the accumulation of that change, or the area under a curve. The fundamental theorem of calculus is the bridge connecting these 2 powerful ideas. It reveals that the process of finding the total amount of change, integration, can be reversed to find the instantaneous rate of change, differentiation. From a practical standpoint, it means if we know the antiderivative of a function, we can calculate the exact area under its curve without having to sum up an infinite number of tiny rectangles. It's an elegant and efficient solution. Thank you for joining me on this journey through derivatives and integrals. I hope you now see their individual power and, more importantly, the profound and beautiful connection between them. Keep exploring, and I'll see you next time.